Hey folks, Todd Coburn here with your Aerospace Structure series. This video is on the micromechanics of a lamina, and this time we're going to focus on the strength of the lamina. How do we predict the strength of a lamina from the strengths of its constituents? Alright, we want to remind ourselves of our nomenclature. Here we see a three-dimensional view of a lamina, and it has stiffnesses that will take axial stresses. We can see we've got axial stresses, shear stresses, and axial stresses in two directions, and shear stress. We can see that in a three-dimensional view here and a two-dimensional view. Positive sign convention means the stress acting on the positive x face is acting in a positive direction. On a positive y face is acting in a positive direction. And for shear stress, positive x face in a positive y direction, positive y face in a positive x direction. And the converse on the other side, while we have positive x for the right side, when we go to the negative x in the negative direction, that's also positive, and so on. Okay, we've got we have the strengths. We're going to call them in this sequence capital F, which is the aerospace sign convention for like an allowable stress. We're going to use 1 for the principal material, one direction, and 2 for the secondary principal direction, and 1, 2 for the shear direction. And then we're going to use subscripts T and C for tension and compression, as you see here. Once again, we're going to be looking at the lamina, and we're going to be looking at the properties of the constituent. We're going to be focused on fiber reinforced lamina, so we're going to have a fiber material and a matrix material. And we're going to use the nomenclature, once again, capital F for allowable. We're going to use a subscript F for fiber, M for matrix, and T and C for tension and compression, as you see here. So our basic concepts, we talked about this, I believe, briefly before. We have a unidirectional lamina, and we're going to see while it does deform plastically a little bit, we're going to actually just look at the linear, pretend that it acts in a linear elastic manner. This little figure from Jones does a good job of illustrating that. Here we see the stress-strain curve for the composite. We see the composite material, that's that middlemost graph. We see that it consists of fiber, which would have reacted like we see here, the upper curve, and matrix, which by itself would act like the lower curve. And we can divide this into stages, as Jones did, with the linear elastic portion, the portion where it starts to go non-linear, and then the part that's more plastic. The first part, we're saying the fiber and the matrix are deforming both elastically. The next stage, fibers are elastically deforming, but the matrix is now deforming plastically. Fibers and matrix both deform plastically, and then the fiber fractures, which will typically result in a failure of the composites. That's the way he defined these stages. Now, the only problem is that's complicated, and so we tend to make simplifications. So we're actually going to evaluate, while this is more analogous with real life behavior, we're going to follow the crowd in making some gross simplifications. Namely, we're going to assume linear elastic behavior all the way through. Okay? So our basic strength concept, we can kind of look at this a little more carefully. Let's go ahead and draw these as if they're linear, which is the way we're actually analyzing it. Once again, we see the stress-strain curve, we see the fiber, we see the matrix. Fiber is the upper curve, the matrix is the next curve, and the composite is the next curve, and the matrix is the lower curve. We see the fiber going up to its fracture point, and then it breaks. We see the composite, which terminates here at F1, because it's allowable. The composite itself is actually picking up linear elastic stress strain. It's going to behave in a stress strain manner linear elastically, or that's what we're pretending, until it reaches that point where the fiber fractures. And then it really can't go any further, because that will immediately be followed by matrix fracture. And so we see that truncate at that same point. The matrix, we're seeing the linear elastic behavior as if it continued on loading, acting by itself. But in real life, it's not going to survive beyond fiber fracture. Okay? And while it is, it's also common that a lot of folks prefer and feel it's more accurate to evaluate strains in composites rather than stresses. There may be some merit in that, but actually the stress approach, and stress is proportional to strain, at least the way we're simplifying everything in these cases, stresses are a little more intuitive for people, because that's what we're dealing with. And you can actually get the same results for most practical analysis. So a simplified approach, though, would be to say that the composite strength, the max composite strain, is the max fiber strain. And that's certainly true, because when those fibers fail, it is very unlikely that the composite, which has failed fibers now, will be able to sustain the load. So this is our kind of limiting case here. So we can set this lower bound this way. If we're saying that the composite can't strain beyond the fiber strain, we then can say that the composite max stress is going to be up to the fiber max stress times its volume fraction. Actually, we're going to use a semi-strain based approach for doing this, as you're going to see here momentarily. So let's take a look here. We've got the here's our curves again, and I'm going to rely on both of Jones's curves here. We can see the actual stages on the one side, and then we can see the linear behavior of the three on the other, like we saw before, where that notable points are the max fiber strength or stress, sigma F max, that corresponding maximum strain, epsilon F max. We've got the matrix max strain, epsilon M max, which we're never going to reach, because both the matrix and the composite itself are going to fail when the fiber does. You can see that the matrix would have reached its strength at sigma M max, and we see that there is a crossover point here, and this is an important point. If you look right here, you see sigma M with a subscript at epsilon F max. So what we're saying is, what is the stress that the matrix can carry at the point when the fiber fractures? That's a key point. So our strength of our composite is affected by our fiber strength, our matrix strength, and our fiber volume fraction. At least it is until the fiber fails. We're going to assume that the strains in the fiber and the matrix are the same, that they act as one, that there's not differences across the cross-section. And we can then write our composite strength like this. When we say composite strength, we mean for the lamina itself, the combination of fiber and matrix. So we're going to use the nomenclature here momentarily. Sigma, the stress, for sub C, which is for the composite or for the lamina. The max value of that lamina strength is going to be, we know it's the maximum strength of the fiber times the volume fraction. We know that the fiber will pick up stress. It's going to pick up stress in accordance with its volume fraction. All of that is going to go up until the max allowable, and then it's going to fail. At that point, we not only have fiber working up until then, we also have matrix working up until that same point. So we're going to go ahead and use this nomenclature, sigma, the stress that the matrix has at that same stress level, that's what we're using here, times the volume fraction of the matrix, which is 1 minus the volume fraction of the fiber. Okay, this is a key equation because we're saying we're getting all of the capability of the fiber plus as much of the matrix as it can sustain at that strain level. This is the actual strength at which the fibers fail, which means that's the last point of the strength of the composite as well. Okay, so we're going to drill down on this concept. This piece is the fiber strength that we see right there. This piece here is the matrix strength at the fiber strain, which is right there. Got that? Okay. Now, we know that the composite strength, the strength of the combination, it should be, or better be, greater than the matrix strength by itself. Otherwise, why are we spending all the work putting fiber in there? And we can take this, equate that, plug in our composite strength equation into this equation and solve, and from this we get what's called the critical fiber volume fraction. If our fiber volume fraction is below that value, then adding fibers actually weakens the composite. That's really a dumb idea, so we need to stay away from that point. Okay, now the other thing is, well, if the fibers fail, then the matrix will probably fail. And that is governed by this equation where we see this, once again, the composite strength better be stronger than the matrix strength once those fibers fail. That's what this is saying. It's taking that point. Now remember, we have fibers, and if they fail, if there are fibers, we're going to have less volume of matrix. That's the 1 minus VF on the right side of that equation. So what this is saying is the composite strength should be better than what that matrix is, whatever's left once the fibers have failed. And this equation can be rearranged to get what's called the minimum fiber volume fraction. If our V sub F is below this value, then the composite fails by matrix deformation and is weaker than the strength of the matrix alone. This means that the composite is even weaker than the matrix was with failed fibers in it, which is a ridiculous place to design. So these two create limits on what the volume fraction should be. We actually kind of want to get that volume fraction as high as we can get it, because that's going to be a more efficient, a stronger, stiffer composite. The only problem is, as you get more and more fiber volume fraction, it can be more and more difficult to get all of the fibers to completely wet, to be completely impregnated by the matrix. The matrix needs to not just bond those fibers together, it needs to surround the strands of the fiber and bond it to itself and press into the fiber and make everything act as a single unit. But these are two lower limits for volume fraction. Okay? All right, so continuing our thoughts here, we have our two graphs. Once again, these are from Jones. We have our two controlling equations, one for the the critical volume fraction, and one for the minimum volume fraction. We're going to drill down on this a little further. Actually, Jones has a really good description of this in his book. Okay? We're going to start by looking at this. This is our strength of the composite, and you're noticing that, remember, we're looking at this up until the point of fiber failure. We see that that equation is the equation of this line. It goes from the maximum, the stress of the matrix at max fiber strain with when there's no no fiber volume all the way up to the fiber strength when everything is fiber volume. That's that equation, okay? This equation does not let us exceed the max fiber strain. That's what that's doing, okay? We have this equation, and what this is doing is that's plotting what the strength of the matrix is. Now you'll notice if we have no fiber, we actually just have, on the left side of this curve, the matrix strength. But as we add fiber, assuming those fibers have failed, all we're getting is more and more holes in the matrix, which means less and less matrix but nothing added because everything that's added has failed. And that's what this line is. So this line, the blue line, is what happens when the fiber has failed. That's the matrix strength after fiber failure. And the green line is the strength of the composites by adding together all the strengths up to the point of fiber fracture. Okay? These two are key lines, and how they intersect give us some insight into these volume fractions. If we move from left to right on the upper blue curve, we see how the matrix strength deteriorates as fibers are added if we are assuming that they have already failed. Also moving from left to right, but now on the green curve, which starts off lower at first, we're showing that we're looking at the composite strength at the maximum fiber strain, which is less than the matrix strength. So we see the fiber, if you add only a tiny, so starting at the left of the green curve, we have no fiber, but we have, but we're only limiting the matrix to the fiber strain, which means the matrix strength, instead of being at this value, we're limiting it at the point where the fiber has failed. So we've actually just thrown away part of the capability, and for no reason, because there's actually no fiber. Now as we add fiber and go up this curve, we're getting more and more strength from it, and we see how the strength of the composite lamina improves as we add more and more fiber. That's the green curve. Okay. Now, we see where these cross right here at the minimum fiber volume fraction. This is where the increasing strength of the composite, or the lamina, due to adding fibers, finally surpasses that diminishing curve from just cutting holes in the matrix. That's what that is. Okay? And our critical fiber volume fraction, which is associated with this point here, is where that increasing strength by adding more and more fibers to the matrix finally passes the original matrix strength. Obviously, it would be really foolish to design below the minimum fiber volume fraction, and it is also foolish to design for anything below the critical volume fraction, because both of them have a negative effect on the strength of the lamina. You have to get that fiber volume fraction above these two values in order to get a benefit from your fibers. And since there's cost, effort, and expense to adding fibers, the whole reason we're going to that is to get more strength. Does that make sense? If this is not completely clear, watch this through a few times and think about these curves. If that's not sufficient, then maybe pull up a copy of Jones. You can take a look at the section where this figure is, and you can kind of study further. He has a fairly good explanation of that. Okay? All right, so now we're ready to develop our strengths. Let's start with the tension strength. Since we're practically there, we've already been talking about it. We can write our tension strength, or our strength of the composite, and actually I'm making this general here, F1, the strength of the lamina in the one direction, is just the fiber strength times its volume fraction plus the composite stress at the max fiber strain times its volume fraction. We've talked about that in the last couple slides. Now, to define where this is, remembering Hooke's law, we know the max fiber strain is just the max fiber strength divided by its modulus, assuming that we're behaving elastically. Okay, no problem. We then can say that the matrix strength at the fiber volume's maximum strain is just the matrix modulus times that strain level. We can plug in the strain level we just calculated, and we get this relation as the fiber strength times the ratio of the modulus to fiber modulus. This gives you that stress level, the maximum stress that the matrix reaches at the point where the fiber max strain is reached. We now can plug this into our earlier equation and write it this way. You can see here we've got, and I've written this now, this general equation now twice, once for tension and once for compression. So this is giving us the one directional strength, the material principal direction strength for tension and compression. Now for tension, this is a pretty good estimate. For compression, this is a fair estimate as well. However, it's not sufficient, because while this needs to be checked, we also need to worry about stability. We'll do that shortly. And we said that. Got that? Okay. Now for our lateral strength, the fibers provide very little help in the perpendicular direction, because that lateral stress for a unidirectional lamina is pulling those fibers apart, which means basically or pushing them together, which is basically working the matrix. So we could just predict that or estimate that as the matrix strength. So the allowable lamina strength for tension is just the matrix tension strength, and the allowable fiber strength in the two direction for compression is just the matrix compressive strength. Okay? These are fair estimates. So let's start thinking about stability. When we think about these fibers, right, if you ever pushed on a fiber, you know they're trying to buckle because they're thin. But they actually so there's a buckling allowable here, but because they're embedded in this matrix, it's like being in a bunch of springs. It's like being, we call that a beam on elastic foundation. It's a beam because it's resisting compression by its bending stiffness, and yet the thing that's resisting it in between the supports is all this material that has an elastic modulus. It has a stiffness that's resisting that motion and helping to resist buckling. That's what we're kind of looking at, and this is a little model of how that might look. Now we can actually do a really loose job and say that buckling of a single fiber like this is governed by Euler's equation, which we all know the first mode will be when the M is 1. That's the first mode. At the second mode, it's 2, and so on. In fact, we use this to develop our compressive allowables for columns, where we found different Ks for different end constraints or midpoint constraints, which drove that buckle shape into higher modes. We saw the same thing or a similar thing when we looked at flat panels, like flat plates and curve plates loaded in shear and compression. So we can actually use Euler's equation to model this. Now if we had if we had no foundation at all, if we only had pinned ends, we would buckle in our mode shape. And actually we'll get the same mode shape if the stiffness of our supporting matrix is really, really low. It still will just go into the first mode shape. But if you keep increasing the modulus of the foundation, keep increasing it, eventually there's going to be, the more this tries to deflect, the more this is resisting. Eventually we'll pull it down into its second mode, which looks like this. Once the modulus of the foundation gets sufficient, it drives it to the second mode. And if you increase it some more, it will drive it to the third mode. And so on and so on. Just like we saw with flat panels with edge supports all around, as we change the edge support, those narrowing the edge supports drives you into higher and higher modes, resulting in higher and higher buckling levels. We got the same principle acting here, but now it's the fiber laying on the matrix of the like epoxy or whatever the matrix material is, which is all embedding it and also resisting it by having like all these little springs hanging onto the thing, and that's how it behaves. You got that? All right, so hold that idea in mind. Remember, we're talking about buckling at higher modes. We're actually not going to derive this, but we've seen that this is how this works. The way these puppies work is like a beam on elastic foundation. Now, there's another principle at work also, and that is the way that these buckles fiber, the way these fibers buckle, excuse me. First of all, we have these being driven into a higher mode. We haven't figured out what that mode is yet. The second thing is the magnitude of the buckle is affected by the phase. So we can actually look at two different models, which we're going to call in phase and out of phase, okay? So here we see in the figure A, we see the fibers being compressed. And then we see two other pictures, B and C. B is out of phase and C is in phase. If you look at this, you see you got the fibers, and in figure B you see that this one's the first one's trying to go this way while the other one's trying to go the opposite way. So they're going further apart and then close together and then further apart. It's like they're completely out of sync. In figure C, on the other hand, you see them sliding, 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 sliding. Okay? So we see out of phase, and in phase. Now you'll notice these result in different behaviors. Out of phase means we're going to be pulling tension on the matrix, and then, right, tension on the matrix, compression on the matrix, tension on the matrix, compression on the matrix, tension on the matrix, compression on the matrix. This is loading the matrix's extensional stiffness. So we're going to call that the extensional mode. The other one you see is going ha 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 ha. You'll notice they're not really pulling apart, they're working in sync. But because they're working in sync like this, you'll notice they're sliding on each other, so we're actually loading those in shear. That would be the shear mode. Okay? So out of phase tends to put the matrix in tension compression. In phase tends to load the matrix in shear. Therefore, this is called the extensional mode, and this is called the shear mode. These allowables for these two modes can be developed or estimated by equating the change in strain energy of the matrix with that of the buckling fibers. This is a bit of an advanced topic, and so we're just going to lean on the results that other folks have developed, and we get these two equations. We're going to call it F for allowable, 1 for mode 1, or the direction 1, excuse me. C for its compression. We're going to use a subscript E and S. E for extensional mode, S for shear mode. The extensional mode can be estimated like this. It's got inputs like the fiber volume fraction, the matrix and fiber moduli, and that's it. And the shear mode has the shear modulus, that makes sense, and the fiber volume fraction. Got it? So when we evaluate our composite lamina, we have to worry about that first compressive strength equation. We also have to worry about these two potential stability equations, and so we should take F1C as the minimum of these three values. We saw the compressive allowable, the ultimate allowable on the prior slide, and now we see the two types of stability mode that are most prevalent. And if we just take all these, take the lowest one, we'll call that the F1C. Okay? All right. This little, here's two more little figures we're going to look at from Jones. The first one is showing how this behaves for a glass epoxy. You see here your extensional mode is plotted, and you see the shear mode is plotted. You'll notice they have a little elastic versus inelastic behavior over at the right end of it. Now, obviously, all we're really concerned about is the lowest allowable here. So we can just follow the lower curve and then follow the next lower curve as we go through, noting that inelastic is probably too complicated for most work that we're going to need to do, and so we just follow the elastic curve. If you wanted to plot this out and look at how it behaves with the theory versus test, this is some data also from Jones where we see a boron epoxy plotted. Here is now where the left curve has the full curves. This one just truncates the curve at the place where they intersect, and you see this extensional mode and the shear mode for two different materials. One is a boron epoxy, that's the upper curve, and the one with these are both boron epoxies, but one is one kind of epoxy, one is another kind of epoxy. Now the important thing here is not the theoretical curves, which we already looked at a moment ago on the left. It's these data points that are lying on the curve. It looks like we're getting pretty good agreement. However, you'll notice first they tweaked the extensional mode a little bit, and secondarily they stuck a fudge factor in there in order to match the data. Well, we can always stick a fudge factor at the last minute to try and make it match, but what that means is that doesn't necessarily translate to all other materials. Once again, I've said in my book and in the lectures, we have to be careful. We've got some represented properties in the handbook to work with and play with, but when we're building composites, we really need to go and get test data. The manufacturer often of the composite materials often has test data. If we do anything different outside what they are testing, then we need to go out and get enough of our own testing to make sure that we understand the behavior of our material. Okay? Shear strength, actually, we can use a rule of mixtures kind of approach and just develop an estimate for the shear strength of the lamina by taking the fiber shear strength times the volume fraction of it plus the matrix shear strength times its volume fraction. Once again, V sub m is just 1 minus V sub f, right, as we've seen in other things. All right, so we can kind of summarize all these equations. We've got our two minimums. We've got our minimum volume fraction and our critical volume fraction. We've got our tension strength in the 1 and the 2 direction. We've got our compression strength, which we have an ultimate value, an extensional stability value, and a shear stability value, which we're going to take the minimum of those three, and then we're going to use, it looks like I left a typo here slipped back into Jones nomenclature. This one on the right, what's called a YC, is actually our F2C. F2C is just that, and that is just the matrix strength. That is just FM. C is F2C. Let's sketch that on here since that's F2C, and this is F of the matrix C. Got that? Okay. And then our shear allowable is given this way. So so we kind of saw how all these were developed, and understanding that is useful for making you stronger. But in terms of what we're going to calculate and do, these are the equations we're going to use for the majority of our composite analysis, at least in this class, and for many practical designs. You get out in a company that's this is usually sufficient, should be good for 60-70% or more of the composite analysis out there. If you get into somewhere that's doing more cutting edge, and you may be delving deeper into more advanced methods to come up with even more accurate methods of estimating. A quick word on a couple other topics. The first one we might want to talk about a little bit is the residual stresses. Okay, when we have compressive stresses, when we're curing, we're going to tend to develop residual stresses. Remember, we've got all these materials and they're different, and they have different coefficients of thermal expansion. That means they expand and contract differently under temperature. And because curing is done at an elevated temperature, you can actually end up locking in stresses, residual stresses, due to the mismatch of thermal, the coefficient of thermal expansion. Now the question is, how much of that is actually locked in? It's really easy to try and be really clever and accurate and come up with a real rigorous approach for calculating the, taking the max temperature change and then assuming all that's residual strength. But when you start looking at the allowables, you find out, oh my gosh, this predicts everything's failing, shows that there's something deeper at work, that is not sufficient for, because what's happening is while you are elevating the temperature, and these do have at different rates and are cooling at different rates, at some point that cooling gets baked in, and then you're getting a stress developed, and how much of that kind of settles in together and how much of that is left as a residual stress is a matter of judgment and potentially quite a bit of testing. But this is one thing we should be careful about and think about. And a lot of times, as long as we're curing these and then testing our cured part, then we don't necessarily need to go and superimpose additional residual stress on top of what we already think we have if our test data already includes something that's been cured in the same manner. If you're curing something and you get all those residual strengths, whatever stresses, whatever they are, and then you go out and you test a failure, and you're measuring those tests, the strength at that test level, and that already has the same level of baked in whatever the residual strengths were or stresses were, then you actually can just go on and just focus on the applied loads without having to get into this detail. However, if you cure the material differently, or if you don't test as rigorously, it's possible that residual stresses can end up causing something you didn't expect, and that can be quite costly and dangerous. So you need to be aware of this and think about this as you are designing your composites. So we can kind of summarize here a little bit. We are talking here again about micromechanics. We've looked at the constituent properties. We've taken the properties, we've used some reasoning with some engineering equations for how those might behave, and we have kind of used our judgment to develop a practical approach to figuring out what the strengths are. And that does a fair job, does a better job for some things, and not as great a job for other things, but it does a fairly decent job of predicting composite strengths. But there's a lot of things that it doesn't account for, and some of these, or most of these, would be different from different composites. Things like non-uniform curing. This can be a function of your thickness or even of your materials. Residual stresses, we talked, just barely scratch the surface of that. Voids, if you aren't wetting out your fiber, or if there are any voids, because a lot of times if you don't get the proper impaction, you don't properly impregnate your fibers, you can end up with voids, and that can obviously undermine, and that may not even be uniform, and that can undermine your properties. Random fiber packing, or how those are aligned, contiguous fibers and misaligned fibers, all these things can change things from what we predicted. While these differences shouldn't stop us from predicting, it should make us a little bit suspicious of our own work until we get some test validation. And test validation often means we have to go test our own composites. Sometimes we can find test data that's similar enough to get enough confidence. And the more broad we see of the usage of a certain composite, we see test data here, test data here, test data there, all these different applications that we're seeing the same trend of strength. Our little composite falls in here. We got the same this is a little different, or right in between here, and you can kind of use some judgment. But when in doubt, you need to do some testing. We have to be careful, because composites, because of all the variances, can involve extensive, exorbitant amounts of testing. However, a good engineer with good judgment and understanding of those composites can often break that down to, no, we can do this direction, this direction, this direction, And with these kind of configurations, we're going to predict up front, see how that behaves, maybe try it in this application here to make sure it played out the same way as we're predicting at the component level, and can cut their cost by using good engineering judgment. Once again, here's a little look at some fiber properties and some matrix properties, such as the ones we have in our handbook in the appendix. This is just some representative values, and there are other texts that provide more information on that kind of thing that we can access for our own designs and industry. So I hope that helped. We now have learned how to look at a lamina. We've learned how to take the properties of the lamina to estimate, the properties of the constituents to estimate the lamina properties, and how to get the strengths, use the strengths of the constituents to estimate the lamina strengths. Stay tuned. We're coming closer to the real meat and potatoes for composite structural analysis.